A BJT, bipolar junction transistor, requires to be operated in active region if one wants amplification from it. Not only that, its operating point requires to be located in a proper place, and it has to be maintained. The operating point has to be maintained, fixed at its designated location. A good bias circuit is one which fulfills all these aspects. Several biasing circuits are in use. Out of them, self-bias circuit is considered as the most versatile and being used widely. It is used not only with BJTs but also with FETs, not only with one or other configuration, but with all the configurations. It has been in use for the last 50 years in the industry, and hence its functioning is well understood. Its design is very well known. In addition to able to establish the operating point at a desired location, it is also be able to provide very good amount of stability to the circuit. Stability implies prevention of drift in the operating point. Drift of operating point is a serious issue in transistor circuits, especially in BJTs, BJT amplifiers. It is a very serious issue. Electronic devices, self-bias circuit, series on semiconductor devices and circuits, lecture number 3.15. Out of all biasing arrangements, self-bias is considered to be the most versatile, and it is considered to be the one which provides maximum amount of stability to the circuit, and for this reason it is widely used in biasing the transistor BJT. While studying self-bias circuit, we encounter two aspects. One is design. Here, operating point is given. We are required to find component values, the values of the components that we can use to establish the given operating point in the transistor. Another aspect is also encountered, that is analysis. Here we are given circuit along with values of different components that are used in the circuit, and we are to determine the operating point, collector current and collector to emitter voltage. In the present session, we consider both these aspects of self-bias circuit, and also we spend some time on stability, amount of stability that is provided by the self-bias arrangement. We begin the session by considering a few points, key points regarding the functioning of the self-bias circuit. This circuit is able to establish stable operating point. The term stable is stressed here, underlined here. Other biasing arrangements, they are also able to establish the operating point at a desired location, but the speciality of this circuit is, in addition to establishing the operating point, it also makes it stable, preventing the operating point from drifting. The current in the resistance Ra in the emitter lead causes a voltage drop which is in the direction reverse biasing the emitter junction. Notice when emitter junction is biased in a reverse way, current drops, base current drops. The increase in IC collector current tends to increase the voltage drop across Ra, decreasing the base current. Hence, IC will increase less than it would have had there been no self-biasing resistor Ra. When IC is prevented from increase, then drift of the operating point is arrested, or stability is ensured. Here is shown the circuit. This is amplifier circuit. VCC is DC power supply or bias supply voltage. R1, R2, these are called bias resistors. RC is collector resistor. RA is emitter resistor. One can see here a capacitor too on the input side. Output side also one can find a capacitor, but here it is not shown. The purpose of these two capacitors is not one but two. First one is to couple the signal. The capacitor that exists at the input terminals, it couples the output of the signal source to the amplifier circuit. Similarly, the capacitor at the output terminals, it couples the signal from the amplifier to the load. Second purpose is prevention of DC entering into the source or entering into the load. Here is VCC, it drives some current like this. If capacitor is not here, it is not there, then this current, some of this current may enter into the source like this. Current entering into the source means spoiling the source. Similarly, DC entering into the load means not only power loss, reduced efficiency, but also it leads to unwanted, unnecessary complications and repercussions. For example, if the load happens to be an audio amplifier, audio loudspeaker, then DC running through the coil of the loudspeaker generates noise, hissing noise. So in addition to reduced efficiency, it also leads to poor performance. So DC is prevented from entering into the load by placing a capacitor here on the output side. In B is shown the same circuit, self-bias circuit, with some simplification. The input part R1, R2, VCC. This part is converted into a Thevenin source with voltage V with resistance RB. Now one point I repeat, R1, R2, VCC. These three together biases collector junction in reverse direction and base emitter junction in forward direction. Now the transistor is in active region. It is ready to work as an amplifier. Here is shown a simplification of base circuit. R1 is there, R2 is there, VCC is the thing. Now this entire thing can be replaced by a Thevenin source with voltage V with resistance RB. V is given by VCC R2 by R1 plus R2. RB is given by R1 R2 by R1 plus R2. RB is in fact parallel combination of R1 R2. Now we consider a few aspects of self-bias circuit with respect to its design. This is very popular, as already mentioned, and being used widely for several decades. So some 40 years, 50 years, one can find this biasing arrangement being in use. Certain practical guidelines have been evolved for its design over a period of time. It has been found that a reasonable compromise between stability, gain, and output swing can be achieved if two criteria are adhered to simultaneously in the design of the circuit. While designing a circuit, several aspects usually are to be taken into consideration. It is not optimizing a single parameter or two parameters. Several aspects, they have to be taken into account, and sometimes we need to compromise in one aspect to get benefit on some other aspect. As far as this circuit is concerned, stability, gain, output swing, these are important aspects normally considered while designing the circuit. Some more aspects regarding design. The emitter to ground voltage should be approximately 1/10 of supply voltage. These are the guidelines that are followed. These are the things that are evolved out of experience over several decades. VE is to be 0.1 VCC. The current through R2 should be approximately 10 times greater than DC base current. To meet this criteria, the input resistance looking into the base must be 10 times greater than R2. However, both the conditions can be met when the relation R2 equal to beta minimum RE by 10 is satisfied. Here beta minimum represents the minimum value of current gain beta. Full name for beta is large signal CE current gain. So its minimum value, beta minimum. It is provided by the manufacturer. Its value can be found from the data sheets. So VCC is available. So VE is available, and when VE is available, RE can be found. When RE is available, R2 can be determined. Some more points regarding the design procedure. The design procedure is based on the assumption that quiescent values of VCE and IC are known constants. Actually, VCE, IC, these are together. Operating point. Operating point is given, and we are asked to find the values of resistors and other components. In most practical design problems, the value of the supply voltage VCC is predetermined by system considerations, and hence it is a fixed known constant. The objective then is to find RC, RE, R1 and R2 that establishes the required operating point and also satisfies the above two design criteria. Actual process. The first step is to find VE using the relation VE is equal to 0.1 VCC. VCC is available. Multiply it with 0.1, so you get VE. Next step is finding the value of emitter resistance, as IE is roughly IC. Base current is very small. Collector current is nearly equal to emitter current, and collector current is available as it is part of operating point. So IE is available. VE is available, IE is available, so RE can be determined as it is VE to IE ratio. Here it is shown RE emitter resistor is VE by IE. It is nearly equal to VE by IC, as IC is nearly equal to IE. As VE, IC are known, RE can be computed easily from this relation. Next step is finding the value of collector resistor RC. Writing KVL around the output circuit. Now let us move to output side of the circuit. Write down KVL. From that KVL, RC can be found as VCC minus VCE minus VE by IC. VCC is available. VCE is part of the operating point, which is given, which is known. VE already we know it is 0.1. VCC. IC is also known because it is part of operating point. So RC is known. Lastly, the values of bias resistors R1 and R2 are estimated. First, the value of R2 is computed. It is beta minimum RE by 10. RE is known, beta minimum one can determine, one can obtain from the data sheets. So R2 now is known to us. Next, the value of R1 is computed. From the input based circuit, one can say VB is equal to VBE plus VE. It is R2 VCC by R1 plus R2. So from this, R1 can be found as R2 multiplied by VCC by VE plus VBE minus 1. VE is known, VBE base to emitter voltage. For germanium, it may be 0.2, 0.3. For silicon, it may be 0.5 or 0.6. Exact values one can have from the data sheets. VCC is known to us. R2 has already been computed. Now R1 can be found within no time. This is the way one has to determine the values of components that goes in the design of the self-bias circuit. Now it is about analysis of self-bias circuit. The voltage divider circuit on the input side at the base, it can be replaced by a Thevenin voltage source with a resistance. The source voltage is V, resistance is RB. V is equal to VCC R2 by R1 plus R2. RB is equal to R1 R2 by R1 plus R2. This part we have already considered. We have already familiar. We have already touched upon in the present session itself. Now, while going further, it is required to be mentioned here that the purpose of analysis is to determine the operating point. Operating point means IC, collector current, and VCE, collector to emitter voltage. After doing simplification on the input side, one can write KVL around base circuit or input side circuit. It results in an equation minus V plus IB RB plus VBE plus IB plus IC RE equal to 0. This is KVL around input side circuit. In this equation, V is there, which is known. VCC R2 by R1 plus R2. VCC is known, available, R1, R2 are available. So B is known, RB is also known, as R1 and R2 values are available. So in the equation, KVL on the input side, V is known, RB is known, VBE is some fixed constant. It may be 0.2, 0.3 for germanium, 0.5, 0.6 for silicon. RE is known, and IB, IC. These are unknown quantities, but IB, IC are connected through IC equal to beta IB. Exact relation is IC equal to beta plus 1, IC naught plus beta IB. If IC not is unavailable, then we can approximate IC as beta IB. Beta is known. So one can write IB in terms of IC by beta. So in this equation, we have only one unknown, that is IC, after IB is replaced by IC by beta. The solution gives us IC, collector current. If IC not is available, then one can use this complete exact relation for collector current. So first two equations together, they are able to provide us collector current. Collector current is one part of operating point. Another part is also there, it is VCE. This part, this voltage, it can be obtained by writing down KVL around output circuit, collector circuit. That equation is minus VCC plus IB plus IC RC VCE plus IE RE equal to 0. In this equation, notice this is known, VCC, RC is known, it is given, RE is known, given, IC we have already calculated. So IC is also known. Once IC is known, IB can be found using IC by beta equal to IB. So IB is also known. Once IB is known, IC is known, IE can be found within no time. In fact, IE is IB plus IC. So IE is known. So in this equation, all quantities are known except VCE. After solving this equation, one can obtain VCE too. Now operating point is available. IC, VCE values are known. This completes the analysis aspect of self-bias circuit. Now we move to another aspect of self-bias, stability. While studying stability provided by self-bias, one equation is of very much helpful. That equation is derived by combining first two equations. Out of these two, first one is equation written around base circuit, KVL written around base circuit. Second one is analytical relation for collector current, output current. Combining these two, one can have a relation given here, RB plus RE beta plus 1 over beta IC equal to B minus VBE plus RB plus RE beta 1 beta plus 1 over beta multiplied by IC naught. This equation we are going to refer while discussing stability factors pertaining to self-bias circuit. Now we consider stability of this circuit. To know how much stable the circuit is, we need to look at three stability factors: S, S prime, S double prime. The definition of S, S prime, S double prime, they can be applied to the equation that we derived in the previous slide, connecting IC naught beta with VBE, and determine expressions for the factors. We get S as 1 plus RB by RE, S prime as minus 1 by RE, S double prime as IC1, S2 by beta 1, beta 2 plus 1. The last expression needs some explanation. What is IC1? What is S2? S double prime is delta IC by delta beta. Small change in collector current by small change in beta. When change is there, after change, one collector current exists. Before change, a different collector current. So now we have two collector currents. The difference is change, delta IC. At these two different collector currents, the transistor usually has two different values for beta. Delta beta is the difference between these two beta values. IC1 beta 1 may be collector current and beta values before change. IC2 beta 2 may be the values after change. So now we have some understanding regarding IC1, some understanding regarding beta 1, some understanding regarding beta 2. Then what is S2? S2 refers to S value when IC equal to IC2. The stability improves with reduction in the value of RB. So RB should be as small as possible. And it increases with RE. RE should be as large as possible. But notice, if you keep on increasing RE, it results in reduction in the gain. Stability gets improved, but gain starts falling down. Also notice, stability is independent of RC. As already mentioned, RC is mainly for the sake of safety. In the absence of RC, what happens is transistor directly gets connected to the source, VCC. Any spurious or sharp changes happen in VCC, then these changes enter into the transistor directly, damaging its performance. A few points regarding silicon and germanium. Notice, silicon is widely used for the fabrication of transistors, electronic devices nowadays. Earlier, it was germanium. Because of some drawbacks, germanium has gone into background. It almost disappeared from the scene, and now it is silicon. Comparison is given between silicon and germanium transistors. Silicon transistors are superior over germanium because for the same change in temperature, collector current IC changes less in silicon. The silicon transistors are more stable when compared to germanium because the drift is less in silicon when compared to germanium transistors. For this reason, silicon transistors can be used even beyond 150 degrees centigrade, whereas germanium transistors can be used a little more than up to 75. So silicon transistors, they can be used up to 175 degrees centigrade, whereas germanium is limited to 75 degrees centigrade. For germanium, effect of IC0 has dominant influence on IC, whereas in case of silicon, ICO is much smaller than for germanium, and it is the VBE that has more influence. IC depends upon IC0, it depends upon VBE, it depends upon beta. In case of germanium, IC dependence on ICO is great, and ICO is also large for germanium, but IC naught is small for silicon. Therefore, influence of IC naught on IC in silicon transistors is not at all dominant. Additionally, he is telling IC dependence on VBE is more in silicon transistors. However, for a transistor with small beta, a large spread in beta may have the dominant influence on IC. With this, we come to the end of this session. In the session, we considered self-bias circuit, its design methodology, its analysis procedure, its stability, along with a comparison of silicon transistors with germanium transistors. Hope this session is useful to you. Soon we meet again with a new topic.